Hello, everyone. Mr. Minix, my name. Math is my game. Today, what we're doing here, and I'm joined with one of my Algebra 2 classes. We're looking at Chapter 2, Section 6. The title is Families of Functions. Families of Functions. And what we're going to do in here is we're going to talk about parent functions. We're going to talk about how functions can be modified. And those modifications to them are actually called transformations. It reminds me of Optimus Prime. Transformers. Borden meets the eye. Wait a minute, what did you just say? I said more than meets the eye. No, it's Borden. I argued with the 10-year-old for 15 minutes about that. Is it Transformers Borden meets the eye or more than meets the eye? Isn't it more than meets the eye? He said it's boredom. Boredom meets the eye. Anyway. Families of functions. We need to define a parent function. A parent function. A parent function, real simple definition. It's a function. It's a function. It's a function from which others are born. A parent function is a function from which others are born. Not Borg, from which others are born. Maybe it is Borgen meets the eye. There's three parent functions in particular we're going to look at, starting with the parent linear function. It goes like this. It says y equals x. Okay? You probably graphed that in Algebra 1 so many times that you could graph it with one hand tied behind your back, blindfolded. Now, in case you're wondering where I'm getting these graphs from, I really don't like tables, but a table of values would probably be the easiest way to think about this graph and where it comes from. I said we're going to look at three of those, so I'm going to get three pieces of graph paper going here. So the definition of the function, it says y is equal to x. So if I think about this for a minute, if I pick an x value of 0, what's the y value going to be? 0. So the graph's going to go through the point 0, 0. If I pick an x value of 5, what's the y value going to be? 5. Now, I did mention that this is linear, and we only need 2 points to make a line. You learned that in the first week of geometry, right? You should have. So technically, I can go ahead and sketch this in with my line. I'll go ahead and make it blue. I said I'll make it blue. So y equals x. That is the parent linear function. Okay. What I mean by that is it's a parent function is we're going to have offspring of it. And if you think about the offspring, it's a band. I don't even know what songs they do. But if you think about offspring, if your folks are your biological parents, you look like them, right? You talk like them. You walk like them. If they're bow-legged, you're probably bow-legged. If they have brown hair, you probably have brown hair. If they have blue eyes, chances are you probably have blue eyes. Maybe not. I don't know. I have green eyes, and neither of my parents had green eyes. Go figure. Maybe I was the milkman's child. I shouldn't have said that. That's wrong. Anyway. But I do look a lot like my dad. Okay. So I guess the point that I want to make here is, we can have offspring. We can have babies of these things that look like it. We might have a line that looks like that instead. We might have a line that looks like that instead. But the point is they are derived from the parent one. Okay, and hopefully we'll have time to address the three different types of transformations and how those ones would come to existence. How are we doing so far? Okay. So the next one then is what we're going to study actually in Chapter 4, and it's called the parent quadratic function. The parent quadratic function. It's defined as y is equal to x squared. I know that you study these in Algebra 1 because I used to teach Algebra 1. If we pick 0 for x and we square 0, what's 0 squared? 0. So this graph goes through 0, 0. That point is actually called its vertex. So the vertex is at the point 0, 0. And if we pick an x value of 1, if we pick an x value of 1 and we square 1, 1 squared is 1 squared is what's 1 squared? Isn't it still 1? Okay? So the graph is going to go through the point 1, 1. What happens if we square negative 1? Negative 1 times negative 1. Isn't that positive 1? Okay? So this graph kind of looks like it's going to be V-shaped, but it's really not. If you remember right, this is parabolically shaped. If you were to square a half, you get a fourth. If you were to square a half, you get a fourth. So the graph isn't quite V-shaped. It's more U-shaped. There's one other point that's going to fit on my graph with integers. That would be the point 2,4 and negative 2,4. Okay? So keep in mind that when you sketch a graph of a quadratic, that the graph really is U-shaped, not so much V-shaped. Okay? So again, keep in mind, that's the parent function. There are offspring. There could be a quadratic function that looks like this. There could be a quadratic function that looks like this. Okay? They're related. They still have some kind of U shape to them. They just might be flatter. They might be, they might appear narrower. Their vertex might be in a different place. Instead of opening upward, they might be opening downward. How are we doing so far? All right? Good. So then the third parent function that we're going to look at is the absolute value function, is the absolute value parent function. And actually in Chapter 2, Section 7, that's what we're going to see in Chapter 2, Section 7. And when we graph it, it looks like that. Okay? It is V-shaped. It is symmetric. It does have a vertex at the point 0, 0. It does open upward. Even though we can't really talk about a slope per se, it appears as though its slope is 1 or negative 1. Okay. So what we're going to do is we're going to take those three functions, and we're going to do like Madagascar says. What's that one song from Madagascar? I like to move it, move it. I like to move it, move it. Wasn't that in Madagascar? Okay. So the name for moving it is actually called a translation. Translation. Okay. So if we had a function f of x, got to answer my phone on the video, you won't miss anything. So this is actually right out of, you know that little meme, straight out of Compton? This would be straight out of Common Core. Straight out of Common Core. You need to know that f of x plus some number k, if you add some number k to the end, what that does is it actually translates the graph up k units. If it's minus k, it actually translates the graph down k units. Okay. What I want you to notice here, what's real important, is where that constant's being added. It's being added on to the end of a function. Okay. A more specific instance of each one of these would be if we had something like y equals x squared plus 6. Okay. That's going to be the parent the parent quadratic function, but it's going to be translated or shifted upward 6 units. Okay. It's going to be up 6 units. If we had y equals x squared minus 8, that's going to translate down 8 units from the parent function. Okay. So what we're doing there is we're kind of tacking on something at the end of it. How are we feeling so far? All right. Now let's think about the Cartesian plane. The Cartesian plane has an x-axis and a y-axis, so we can move something up and down, right? But couldn't we also go the other way, right and left? Here's the one that really messes people up. If we have f of x inside parentheses, and we're adding or subtracting k, it's kind of weird what happens if we add k, and we're assuming k is kind of a positive number. If we add k, that actually translates something to the left. If we subtract k, it actually translates the thing to the right. So I'll give you a second to write that down. Again, keep in mind here, what's real important is the fact that inside our grouping symbols for our function is where we're adding or subtracting something. So what we've got here is something like y equals the absolute value of x minus 5. That would translate the absolute value function which way? 5 units to the 5 units to the if you can read the way I annotated this, it translates to 5 units to the right. 5 units to the right. Okay? 5 units right. Similarly, if we had y equals the quantity of x plus 2, the quantity squared, that would be translated 2 units which way? To the left, to the left. 2 units left. Okay? So, what this is called then, this is called a horizontal translation. Okay? This is called a horizontal translation. Horizontal translation. The previous slide was called a vertical translation. A vertical translation. On an upcoming unit test, a really nice essay question might be, explain all the transformation types. Be sure to include a discussion of translations, reflections, and stretches and compressions. Okay. So vertical translations, we're moving the graph like Madagascar to the right, to the left, to the up, or to the down. What do we think? I know this is a lot, but we got a lot more to go. So here goes. The other kind of transformation is a reflection. A reflection about the x-axis, a reflection about the x-axis. We're not going to look at the one about the y-axis today, but we'll look at a reflection of about. In this context, the word about means around. It means over. It means across. Okay? So in that context, the word about means around, over, or across. So what we do here is we take the negative f of x. Okay? In other words, a specific example would be if we had y equals negative the absolute value of x, or if we had y equals a negative x squared. What the graph of those look like, it's pretty interesting. You know, the parent absolute value function is a v that opens upward. Well, its reflection is a v that opens downward. Otherwise, it looks the same. It's just flipped over. Its vertex is in the same spot. Same thing with the quadratic function. Instead of opening upward, it opens downward. Okay? So we've seen two kinds of transformations so far. Transformations that are called translations, where we move the graph to the right, to the left, up or down. And then transformations where we flip something over or reflect it across the x-axis. Okay? Now, it is possible to reflect something across the y-axis. But I don't want to look at those today. Because the parabola and the v, the absolute value, they're symmetric, so it's really kind of hard to see with those. Okay? So the third and final type of transformation we're going to look at today then is if k is bigger than 1, we have k times f of x. What that transformation is called is that's called a vertical. You might do this before, you should do this before any kind of physical activity, before karate, before you go swimming, before you attempt to jump up and touch the rim. What might you want to do? Stretch, yeah. It's called a vertical stretch. Okay, it's called a vertical stretch. Then the other kind, if k is between 0 and 1, if k is between 0 and 1, again, it's k times f of x. This one's the opposite of a stretch, and some people use another s word, but actually a c word is better. This is called a vertical, a big c word, ends with m. C, actually it ends in n. Has an m in it. What's it called when you squish something down? When you compress it. So it's a vertical compression. A vertical compression. Okay. So a specific instance of this, if we had something like y equals 2x, what that is that's a vertical stretch. That's a vertical stretch. Vertical stretch by a factor of 2. By a factor of 2. By a factor of 2. In other words, it's going to take all the y values and make them twice as large as they had been. In other words, it's going to take the line and increase its slope. It's going to double its slope. If we had something like y equals 1/16 x squared, that's a vertical compression by a factor of 1/16. That's a vertical compression. That's a vertical compression. A vertical compression by a factor of 1/16. What it's going to do to the y values of the parent quadratic function is make them 1/16 as high or as tall as they used to be. In the case of the line, it simply makes the line steeper. In the case of the parabola, it's going to make the parabola flatten out. I kind of sketched that poorly, but it's going to make that parabola kind of flatten out. Okay. Some people might argue that it makes the parabola wider. Actually, it decreases the height of the y parts of the coordinates. So, what do we think? I know that was a lot to throw at you in 10, 15 minutes. Let's take a look at some of the 2.6 Math Excel homework then. So Math Excel 2.6, here we go. See if I can make that a little bigger. For some reason, my computer screen kind of isn't so small, isn't so big. So I've got y equals x minus 7. How does that compare to y equals x? Each output is 1/7. No. It's 7 times. No. It's 7 less than. Yeah, 7 less than. Well, that's not so bad. Each output is 7 less than it was before. Good. What's the graph going to look like? It's going to look like the parent function, which was a slanted line, but it's going to be x minus 7. Isn't that going to be down 7 units? So which one should this be? Should be number B, huh? Should be number B. There we go. All right. Moving right along to number 2. So they've got this function. They want to know when x is 3, what's y? When x is 3, it looks like y is 1. And when x is 5, it looks like y is 2. And when x is 7, it looks like y is a half. And when x is 9, it looks like y is 0. Oh, I didn't do that right. Try that again. I guess because it's 3, 0, huh? Try that again. 3, 0, I had the 5, 2, I think. I think that was okay. There we go. So what happens if we have x plus 2? What I want you to notice here, a lot of people are missing this one when they're trying this. Look at the table. In the table, they already accommodated the x's. The y coordinates or the f of x's in the table are going to be the same. So here we're going to get a 2 again, or a 0. We're going to get a 2. We're going to get a half, and we're going to get a 0. Okay, a lot of people were missing that one. They were having trouble with that one. So what's the graph look like? It's translated left 2 units. It's translated to the left 2 units of the blue one. So there's that. Okay. Vertical stretch by a factor of 6. It's 6 times x, or 6x. There we go. What do we got here? A vertical compression by a factor of 1/6. That's going to be 2 times 1/6 times x. What's 2 times 1/6? That's 2/6, or wouldn't that be 1/3? Wouldn't that be 1/3 x? No, I did something wrong. Oh, and they want it to be a reflection on the x-axis too, so I guess I got to make that a negative. There we go. I didn't read that part. I'm a horrible reader. So anyway, hopefully this should get you in the right direction on the 2.6 homework. It's been real. It's been fun. I'm going to give a shout out to the future Mr. Minnick for being such a great guy. Any other shout outs? Going once. Going twice. Well, that's it. Have a great day. See you.